Based on the cohesive element theory, people have developed this cohesive element, which is a special type of element to model cohesive crack propagation. It is a zero thickness element. It basically represents an interface. Upon loading, the two surfaces of the element separate by the separation can be represented by a vector delta. So this interface has a coordinate system where n is the normal direction and t and s are the two tangential directions. Upon separation, traction would develop to connect the two surfaces. And when you separate the two surfaces to a certain extent, then damage would start to occur and the traction would start to degrade. This is represented by these cohesive laws. So mode 1, which corresponds to opening along the normal direction, have this kind of bilinear cohesive law. When the opening arrives at a certain critical level, or the traction reaches the critical strength of the interface, damage starts to occur, and then your traction would start to decrease. As your opening grows, the traction decreases further, and upon reaching a certain critical level of opening, the traction reduces to zero. This is a similar story for mode 2 and 3. The difference here is on the negative part of this curve. When delta n is negative, it means that now we have compression. The two surfaces are in contact, and damage doesn't grow under contact, under compression, so this part of the curve follows the original stiffness. However, for shear, we don't have the same effect. You can shear in both directions, and damage could accumulate in both directions. The loading unloading curve for shear would be that once we reach the critical shear strength, we start to decrease, and then if at a certain point we unload, it goes back to origin, and then we can load in the opposite direction. It would follow the current stiffness after degradation, and we keep loading it. It will follow this part of the curve until degradation is complete and the traction shear stress reaches zero. Note that this part of the curve, which rises from 0 to the strength value, similarly for mode 1, this part of the curve is entirely artificial. It is represented by a penalty stiffness, in fact. So this is because we want to simulate a perfect bonding behavior before any failure onset. And we can't do it with a cohesive element without a penalty stiffness, because otherwise it would be just a straight rising curve until the strength value. But this would correspond to a stiffness of being infinity, which no computer program could handle. So we have to allocate some stiffness to represent the rising part, where the stress goes from 0 to the critical level. This stiffness needs to be large so that we can have just a small bit of opening before failure onset. It can't be too large, otherwise we have EO-conditioned global stiffness matrix. I'll talk more about this, how to set this penalty stiffness later. Cohesive elements, they are interface elements, so you can't use them to construct your overall geometry. Their purpose is to simulate debonding or crack propagation. So it needs to be kind of inserted in a mesh before analysis most of the time. So for instance, if you could place cohesive elements between plies of different fiber orientations to simulate debonding or delamination, and if you know where the crack is going to propagate, then you could place the cohesive elements there. For instance, in compasses, you know that the matrix cracks propagate along the fiber direction. Then you could consider placing cohesive elements along the fiber direction. Cohesive elements, they work with a damage variable d, and this damage variable could take a value between 0 and 1. And then the constitutive tensor C, which relates our traction with the separation would be a function of this dimensional variable d. How it works is that, for instance, in the mode 1, when we have opening, which means delta n larger than 0, we degrade the mode 1 penalty stiffness by 1 minus d. When d equals to 0, this means this term equals to 1, and we retrieve the original penalty stiffness. When d equals to 1, which means that the element has been completely damaged, then this term, stiffness, goes to 0. Under compression, however, we do not apply this degradation, so that we always have the original penalty stiffness to prevent overclosure. For shear, we apply the degradation regardless of the sign of the shear opening. How do we determine the value of d based on the available information? Taken a generic bilinear cohesive law, this could correspond to either mode 1 and the opening, or the mode 2 or 3. At a certain level of loading, at a certain level of opening delta, I know that I have this stress value, 1 minus d times penalty stiffness times the current opening. My objective is to express d in terms of the opening. This delta would be related to the nodal degree of freedom vectors of my cohesive element through a shape function interpolation. There are several parameters that I can determine easily. So here delta 0 is simply tau c divided by k, which is my original penalty stiffness, and delta f, the opening at the final failure, is the area of this triangle divided by the height, which is tau c, and the area of the triangle is so the area of a triangle multiplied by 2 is 2 times gc. Gc, the fracture toughness, it could be mode 1 or 2 or 3. And I use the geometry here. So if I look at the geometry of this triangle and this larger triangle, so from geometry I know that this length divided by this length equals this length divided by this length. So I have 1 minus d times k times delta, which is this length here, divided by k times delta 0, which is this length here, equals delta f minus delta, which is this part from delta to delta f, and then divided by delta f minus delta 0, which is this part. Based on this relationship, I can then calculate 1 minus d. I cancel out k and then move delta 0 to the right side, and then I can calculate d. So now I have an expression of d in terms of delta f and delta 0, which are determined based on material parameters, and then I have my delta, which I can obtain from nodal degree of freedoms through shape function interpolation. So now I have calculated my d in terms of delta, which is opening, and this relationship is valid for pure mode loadings. And one thing to note is that the damage variable represents irreversible process, so it cannot reduce. If damage variable starts to reduce, it means that the material is healing, and this is not most of the time not the case. So in general, we set that in coding we set that the damage variable can only increase, not decrease. These are valid for pure mode. What about mixed mode? For mixed mode, people have invented a similar cohesive law, but drawn based on equivalent mixed mode quantities. So here delta m and tau m, they are scalar quantities that take into account of the mixed mode loading. So delta here is a vector. It has in general 3 components, and delta m here is a scalar. It's a combined representation of our delta vector and the mixed mode loading cases. And also we need to determine when does the damage starts to occur. At this point, How do we determine the failure onset point based on our current stress state, our Cauchy stress tensor tau? Suppose that we load the interface under mixed mode combined loading. We have mode 1 and mode 2, and then the stress would rise. And one criteria to determine the failure onset is the quadratic interactive stress criteria. We have tau NC, tau SC, and tau TC being the critical strength values for the 3 directions of loading. And then we have tau N, tau S, tau T, the current stress values. And note that this bracket here indicates that we are only taking into account of the positive part of the normal traction, because the negative part contributes to closing the crack, and it does not contribute to failure. When this criteria is satisfied, we say that now the damage starts to initiate. This is sometimes called the damage initiation criteria. Then we need to define equivalent quantities. So having decided when does this happen, we need to define the equivalent quantities like tau m and delta m. We start with delta m. Delta m, we can represent it as square root of the sum of the squares of the components of our delta vector. This is simply the vector delta dot product with itself. This is the L2 norm of our delta vector. Now again, in the normal direction, we only take into account the opening part. To obtain the equivalent traction, we use this relationship, which means that whatever equivalent quantities for traction and separation that I invent, they must satisfy that the product of equivalent traction and equivalent separation equals the dot product between my traction vector and separation vector. This is a measure of energy, and this would mean that they are energy conjugates. Based on this criteria, I can then express Tm in terms of this strain energy divided by our previously defined delta m. At damage onset, there are several information I can collect. I can collect the strain energy components along normal and the 2 shear directions, and also the total strain energy, which would be the sum of the 3. I can also calculate the ratio of the normal and the 2 shear directions in terms of with respect to the total strain energy. Now, with this information, I can proceed to calculate the total area under this triangle, which is the mixed mode fracture toughness. Here I make some assumptions. One of the assumptions is that the mixed mode fracture toughness equals the total energy dissipation when this happens. This is when this is satisfied, we have a total failure. So this GNC would correspond to G1C, and GS and GTC are the mode 2 and 3 critical, the fracture toughnesses respectively. We say that when fracture happens, which means the complete fracture, when this criteria is satisfied under mixed mode loading, the corresponding equivalent mixed mode fracture toughness would be the sum of the energy dissipations along the 3 directions. We make the assumption that the mode mixity does not change much along the loading. Then we can divide this equation on both sides by GMC raised to the power of alpha. Alpha here is a material parameter. It's called a power law exponent. If we divide the equation on both sides by the GMC raised to the power of alpha, and we know that GMC equals to G total at the point of failure, which is when this equation is valid, then we obtain this equation. We retrieve our ratio Rn, Rs, and Rt on the left side, and on the right side we have this expression. Then we can express GMC in terms of the material parameter and the ratio defined at failure onset. This is the definition of a mixed mode fracture toughness based on power law. So here we have defined the point of damage initiation. We have defined, based on power law, the area under this triangle. If we know the penalty stiffness, we then calculate we can then calculate the delta 0, which corresponds to effective separation at the point of failure onset. We can calculate delta F if we divide the area of a triangle by this effective attraction at the point of failure onset, and then we can then proceed to use this equation to update our damage variable along every increment of loading. And again, our damage variable can only grow, it cannot reduce. There is a different, also popular formula to define mixed mode fracture toughness, which is called the BK criteria. This is motivated by the fact that most of the time we observe the two shear directions, T and S, are quite similar to each other. So they have very similar values in terms of fracture toughness and the behavior. So we just define a total shear component being the sum of the two, GS and plus GT, and the ratio of this shear component with respect to the total strain energy at the point of damage onset is defined as B. Then we can use this B together with a BK exponent, which is again a material parameter, to immediately define a mixed mode fracture toughness being GMC. So it's a interpolation between G1C and G2C. So this has been very popular. So once this is defined, then this cohesive law is fully defined. Now I would like to talk about how to set the penalty stiffness. I've only briefly mentioned that the penalty stiffness serves to approximate perfect bonding before damage initiation. It needs to be large so that we have a very small amount of opening before damage initiation. It can't be too large, otherwise our stiffness matrix after assembly becomes ill-conditioned. So what is the right balance then? Let's take this simple example of just a block of material and the uniform tension. It has a height h and Young's modulus of E. Then it will the top surface would have a displacement of capital delta, which is equals to this expression. What if I want to model a crack propagation within this material? Let's say I know that the crack is going to happen here, and I put this cohesive element before analysis. Then I load it. Because the cohesive element has a penalty stiffness, it would also open up a little bit by a small delta. So the overall displacement of the top surface would then include both capital delta and small delta. And this small delta equals to sigma divided by K. K is our penalty stiffness. The objective is to ensure that small delta is much smaller than capital delta. And using this inequality and these two equations, we can relate K and E and also H. We can arrive at this expression to say that K must be much larger than E divided by H. A practical rule of thumb is to set it to be 50 times this, E over H. Note that the unit of K is Newton per millimeter cube, because E has a unit of Newton per millimeter squared, and then we divide it further by H, which has a unit of length. This is because K, although it's called the penalty stiffness, it actually relates traction with separation. Separation has a unit of length. Now I would like to talk about the integration of a cohesive element. Having defined the cohesive law, it's time to integrate the cohesive element to obtain the element stiffness matrix, the internal and external force vectors. Let's write the equilibrium for this cohesive interface under such loading and boundary conditions. We have externally prescribed loading on the top surface of the cohesive element. Cohesive element is an interface element, so it does not have volume. It is characterized by a line, so we perform a line integral on gamma. The left part is the internal virtual work done by the internal traction tau with respect to a variation of our separation vector. And this is the external virtual work with respect to a variation of our separation vector. We can then do our finite element discretization. We write delta in terms of a shape function multiplied with our degree of freedom vector. And we also write our tau traction through the constitutive relationship with respect to delta, and we substitute the mean. We can get this expression. The left side is our internal force vector, the right side is our external force vector, and within the bracket is our secant stiffness matrix, which is always positive. The secant stiffness matrix is a function of A because it is a function of D, and our damage variable is a function of delta, and delta is a function of A. So damage variable is a function of a nodal degree of freedom A, and hence this secant stiffness matrix is also a function of our nodal degree of freedom A. This secant stiffness, because it's always positive, so this is a preferred choice for element stiffness matrix for cohesive element. Once we have this expression, we need to perform the integral on gamma, and we do, when it comes to integration in finite element method, we always do a quadrilateral. There are two popular options. One is the Gauss integration, where we have the integration points away from the two end nodes. The other one is Newton-Cotes integration, where we have the two integration points directly above on the two end nodes. The Newton integration is usually the preferred choice in standard finite element method, but when it comes to cohesive element, it has a certain drawback. In a case where we have one failed element and one failed integration point and one intact integration point, it may occur that you have this kind of artificial interpenetration because of this scenario. When you have the integration point, you are calculating the stress and strain there at this integration point, which means that the whatever constraint you have, such as the high penalty stiffness to prevent overclosure, is only active on these integration points. That is why you could have interpenetration on the two nodes and the Gauss integration scheme. And the Newton-Cotes integration scheme, this problem is however prevented, because now you have the integration points directly on the nodes. However, when it comes to evaluating the internal force vector and external force vector, Gauss integration is usually more accurate, but because of this problem, many people favor Newton-Cotes integration for cohesive elements. When we have the same number of elements in the mesh, Gauss integration would have more integration points, because now if imagine you have a neighboring elements, they are sharing the same node and hence the same integration point. You have 3 integration points in the case of 2-element mesh, and here you would have 4 integration points. Another important issue about cohesive element is the proper selection of element size. In the cohesive zone model, we have a rising part of the stress, and then it starts to decrease. Depending on the size of the cohesive zone and the level of critical stress, this part of the curve could be very steep. And if you use very big elements, for instance, one node around here, and the other node very far at the back, what you get from your evaluation at the integration points and the interpolation using linear shape functions is a very underestimated internal force and external force vectors. So the internal force vector, which you evaluate at this left end and the right end, misses the entire rising and following part of the curve. The rule of thumb is to always have a minimum of 2 elements within the cohesive zone. But the natural question is how to estimate the cohesive zone. Unfortunately, most of the analytical formula do not work well in predicting the cohesive zone, and many times we rely on mesh convergence analysis. It depends on many factors, not only these material properties, but also the geometrical properties of your structure. For carbon fiber reinforced composites and the mode 1 delamination, this cohesive zone size can be smaller than 1 millimeter. Usually mode 1 factor is usually the most stringent requirement. The cohesive zone size for mode 2 and 3 are usually larger than mode 1, that in mode 1. Cohesive elements have many applications. It could be used to model delamination between plies of different fiber orientations. It could be used to model interface debonding between fiber and the matrices. It could be used to model the debonding of a scuff repair patch. Here, the cohesive element would be inserted to represent the adhesives. It could also be used everywhere in the mesh, in between every two elements. In case where you don't know a priori where the crack is going to occur and how does it propagate, what you can do is to make a very refined mesh and then put cohesive elements everywhere. But this is very costly, and still the crack propagation path is constrained to follow only along the boundaries of the elements.